a curve fitting, right? So I would just reiterate the data here and then we proceed further. So we had X and Y data as follows. So this is the XY data, and we are asked to find a curve fit, assuming that it is a linear fit. And we are asked to find the fit at 95% confidence level. And we are also asked to find the goodness of fit. So I said that a linear curve can be written as y equal to ax plus b. And then we had found a to be 1.04 and b to be 0.02. If you look through your notes, this is what we had found. And then we had to find out the R square value. And we found the R square to be 0.99, right? And we said that if R square is close to 1, then you can see it is a good fit. So in this case, R square is very close to 1. So this is indeed a good fit. Now, you can also find the standard error between the fit and the data. Standard error between the fit and the data, meaning when you plot X and Y, so you have these data points which are looking like this. So you have 5 data points, and then you have found a fit. The question is, so each data point and the fit has some error, right? So how do you find the standard error between the fit and the data point? So that means your y equal to x plus b plus minus something, which is basically the error. Okay. So the standard error of the fit SYX is represented as YI minus YCI. This is basically your curve fitting. The difference between the actual data, this is YI, this is YCI. Difference between the actual data minus that predicted from this curve fit, square of that, and to sum it off over I equal to 1 to n divided by the degree of freedom square root. This is the formula that is used to find standard error between the fit and the data. Okay. Now, what is degree of freedom in this case? When we find the standard deviation for a small data set, we said that degree of freedom is just simply n minus 1. But in this case, the degree of freedom is taken as the number of data points minus m plus 1. Okay, here n is number of data points M is the degree of the polynomial. Polynomial fit. For a linear equation, the degree of the polynomial is 1, right? So in this case, the degree of freedom, the number of data points is 5 minus the degree of polynomial is 1 plus 1. So that will be equal to 3. Now, this is the SYX. So for each YI and corresponding YCI predicted from here, you can find the numerator and divide by the degree of freedom and you take square root. And if you do the calculation, which I am not doing, you can check that this will come out to be 0.16. Okay. Now this is the standard error between the fit. Okay, but what you actually write here is the random uncertainty. That is
Excuse me, sir.
T, yeah.
Sorry for disturbing, but I couldn't quite follow as to how we calculated the degree of the polynomial fit.
So degree is basically the exponent of x here. Okay. So if you have y equal to ax plus b, the degree of polynomial is 1. The power of x is 1. If you have y equal to x square plus bx plus c, the degree of polynomial is the highest order of x, that is 2. Right? If you have x cube plus bx square plus cx plus d, highest order is 3. Okay. So it is basically the highest exponent of x, which is the degree of the polynomial of the fit. Okay.
Thank you, sir. Sorry for disturbing.
Sir,
so this random uncertainty we have found, right? It is nu p sx divided by square root of n. So we have to evaluate this. So we have already found sx, sorry, this is syx. Syx already we have found. N already we know. So only thing we need to find out here is the T nu p. Here degree of freedom is 3. Probability is 95%. Okay, so 0.95. So if you go to your T distribution table, you can read this as 3.18. Okay, you can check that from table, T distribution table. Find your random uncertainty, which is T nu p syx over square root of n. That is 3.18 into syx is 0.16 divided by square root of 5. That is 0.23. So essentially, your data is all over the place. So if you want to characterize this error in the curve fit, you have to say that your curve fit is 1.04x plus 0.02. This is what you find from here. But now there is a standard, the random uncertainty of the fit, that is plus minus 0.23. Okay.
So just you need your thoughts. I understand the curve fitting and everything and the degrees of freedom.
Yeah.
But my understanding is it's about like we can also choose the single degree of freedom, right? Instead of 2 degrees of freedom, the curve, it is upon us to decide, right? Like which curve we would like to choose, right? So
Yeah, so here it is given that it is a linear fit. So your m is equal to 1. But if you have the freedom to choose the type of fit, you can use a quadratic equation also.
Agree. Yeah.
Okay.
And
In that case, the equation itself will change, the degree of freedom will change, the random uncertainty will also change.
yeah. And so the random error will reduce, correct? Like
It may reduce or increase because you do not know, right? If the data is linear and if you use a quadratic fit, then you'll see that the error will increase, right? Your R square will be very small. That means it is not a good fit. So if your data is following certain trend, and if you use some other curve fit, the error will be huge, isn't it?
Agree, sir. Agree. Yeah. Sure. Thanks for the clarification.
Since R square for a linear fit is 0.99, that means the data is really linear. But if you use a quadratic, you can do that for yourself. If you use quadratic, you will see that your the fit will not be actually a good fit, and hence the standard deviation of error will be very large.
Sure, sir. Sure. Thank you. Yeah.
So I think we also talked about polynomial fit in the last class. I will just reiterate that. But there is one thing that was missing, which I wanted to talk about. So in polynomial regression, we talked about that y fit should be equal to, let's say, a0 plus a1x plus a2x square. Then we get set of equations, right? I think I had listed down in the last class. That is a2 sum xi4 plus a1 sum xi cube plus a0 sum xi square xi square y. Then you have a2 cube So you basically have these three equations coming from when you find the sum of squares of error and you take, let's say you define a parameter d, which is yi minus yci square sum I equal to 1 to n. Which is yi minus there, and you minimize that dd over dA not equal to 0, the least square method. So each one of these will give you a corresponding equation. So by solving these three equations, you have three unknowns, so you can find for a2, a1, and a0. Depending on your data, you can find out. Now, what I did not talk about last class, which I wanted to talk, that in case of a quadratic fit or nonlinear fit, a fit that is nonlinear in general, for a nonlinear fit, how do you know that whether the fit is good or not? Okay, how good is the fit? So basically, you find out two things. One is the sum of yi minus yci square. This is basically the curve fit at a particular xi. What is the actual yi and what is predicted by the curve fit. The difference between the two, square it and do that for each of these i's. You also find out yi minus y mean square, and you sum equal to 1 to n. Okay. So for example, in this case, if you add 1.2 plus 1.9 plus 3.2 plus 4.1 plus 5.3 divide by 5, that will give you the mean value of y, right? So here you basically find yi minus the y mean of y mean is basically sum of yi divided by n. That is the definition of mean, which you already know. Now the left hand side basically represents the deviation of the data with respect to what is predicted by the curve fit. Okay. The right hand side depicts the deviation of the data with respect to the mean. Okay, and square of that. For a fit to be considered good, the left hand side should be less than the right hand side. That means the scatter of data with respect to its with respect to the mean is to be compared with the scattered of data with respect to the regression curve. Okay, the scatter of the data with respect to the regression curve has to be less than the scatter of data with respect to the mean. So in that case, we have a slightly different representation of R square. So we represent in the nonlinear case R square equal to 1 minus yi minus yci whole square divided by yi minus y mean whole square. So you can see that when the numerator is very small compared to the denominator here, okay, when this is very small compared to this term, this entire term would become close to 0. In that case, R square will become close to 1. So when the data with respect to the regression curve becomes much smaller, square of that becomes much smaller than the scatter of the data, which is the mean, then this value becomes 0. So R square becomes equal to 1, and in that case we can say it is a good fit. Okay. So this is something I did not talk in the last class, so I just wanted to add that. And there is one more thing I need to talk before we move on to the next topic, that is multiple linear regression. So far we have been talking about regression where we have one dependent variable and one independent variable. What if we have one dependent variable but more than one independent variable? What do we do in that case? So that is known as multiple linear regression. So let's say one example is, in heat transfer, the Nusselt number is a function of Reynolds number and Prandtl number, right? It will be some constant times Reynolds number to some other constant and Prandtl number to the power some other constant. So let's say you are asked to relate Nusselt number with Reynolds number and Prandtl number, right? So you have two independent variable and one dependent variable. So one way to take care of this kind of fit is to linearize the equation. So if you take logarithmic on both sides, this nonlinear equation, the power form becomes linear. So you have log of A plus B log Reynolds number plus C log Randall number, right? If you take logarithmic, log A into B into C becomes log A plus log B plus log C. And then if you have log Reynolds number to the power B, it should be B log RE. Okay. So this is just an example, just to relate to, heat transfer application. How Reynolds number, your Notion number is a function of more than one variable. Okay. But in general, you say that you have a variable Z, which is a function of X and Y. Let's say AX plus BY plus C. Okay, so Z is a function of X and Y. Your X, Z is dependent variable. And X and Y are independent variables. And your A, B, and C are fitting parameters. So you must find the value of A, B, and C. So you can use the least square approach, right? So the sum of squares of error has to be minimized. Sum of squares of errors can be minimized. Let's call this as D, which is for a particular I, you have the actual data, Zi, minus the data from the fit, AXI plus BYI plus C, square it and sum it over different I's, I equal to 120. So if you want to find A, B, and C, you need to minimize D. So that is DD over DA equal to 0. Then you have DD over DB is 0. And DD over DC is 0. So from these three conditions, you get three different equations. So what are those equations? So first condition will give you A sum of xi square plus B sum of xi yi plus C sum xi will be equal to xi zi. Similarly, the second condition will give you A sum of xi yi plus B sum of yi square plus C sum of yi is sum yi zi. The third condition would give you A sum of xi plus B sum of yi plus C times n will be equal to sum of zi. So these three equations need to be solved to get the values of A, B, and C. So once you have the fitting parameters, you have the curve fit. Okay. Now, unlike the linear case and the quadratic case, when you have multiple independent variables, you do not have a specific formula to check for the goodness of fit. Okay. And in this case, the goodness of fit is basically tested by what is called the parity plot. I will talk about what is parity plot, taking an example of multiple regression. So let me write down the data. Let's say I take an example. Let's say I have 5 data points and I have the corresponding value of X and Y and Z. Let's say 1, 2. So I have 5 data points. Seven, 6. So I have the data sets like this. Okay. So Z is basically a function of X and Y. And I do certain experiments where I vary X and I get the corresponding, I have for a given X and given Y, I read the value of Z. Okay. So for every X and Y, I have a value of Z. Now I'm asked to find a fit. Okay, find a curve fit and check the goodness of it. How good is the fit? So first of all, we need to find the curve fit. So using the formula that I just wrote, I'll have 3 equations and I can solve for ABC. So if I solve for ABC, you can check for yourself that A will be minus 308, B will be 13, and 435. That means your equation is going to be Z. So Z is AX plus BY plus C, right? So Z will be minus 308 into X plus 13Y plus 435. Okay. Now, how do I check for the goodness of it? I do what is called a parity plot. So on the x-axis, I have Z data. That means these values. This is basically our Z data. In the x-axis, I have Z fit. So this is basically Z fit. Now, for a given X and given Y, I have the Z data. Now, if I substitute this X and substitute this Y, I will get the Z fit. Now, I have the Z data and I have the Z fit. So for a Z data and Z fit, I locate the point. Yeah. Similarly, the next data point, I have Z data. I will have the Z fit because I can substitute this X and this Y. So I have the 6 data. Similarly, I have 5 data points. Now, when I join these data points, okay, if this angle is 45 degree or close to 45 degree, then I can say that my fit is good. But if the fit deviates, let's say I get a curve something like that or something like that, then in that case we can say that the fit is not good, because the Z data and Z fit are very different. They do not agree with each other. Okay, so this is called the parity plot.
Sir, you mentioned this angle 45 degrees, right?
Yeah.
So will there be like a threshold plus or minus, which is like an acceptable range, like 46?
Yeah, I mean, that is something that you have to judge. I mean, if it is, plus minus 10%, typically, you can say that, okay, it is the allowable limit, so you can
So that is
tolerate
subjective,
it.
entirely
Yeah,
dependent on the user.
yeah, depending on, really, how much can you tolerate, really, Okay, so with that, I think, we have talked about regression. Next, I want to move on to a different topic, which is known as design of experiments. Okay, so let's talk about.
Sir, will you be just going through the revision after this topic? I'm just.
See, normally, as I told, that before the midsem, I would. Okay, normally we
Right.
do not do revision, after each topic in
No,
IIT.
only
Even,
brief review. Okay, sir. That's fine, sir.
yeah, even before the midsem also, we don't do any revision. But
Right.
since you have asked before the midsem, I would probably spend one class and talk about, what all we have covered.
Yours.
Okay,
Sure.
but
Thank you
we
so much.
don't really do after each chapter as such. Okay, so I will do that. I think the midsem we will have a revision class.
Sure, sir. Thank you.
So design of experiments, first of all, what is the goal of experiments? So I think in the very first class, we talked about why we do experiment. One of the reasons why you do experiment is that we want to understand the behavior of a system. So essentially, we want to collect data, but we want to do minimum number of experiments, and we want to maximize information about a system. Okay. See, if you want to say that, okay, I want to understand how an engine is working, right? How does it, how the performance varies with, the oil flow rate, the fuel flow rate, temperature, pressure, various parameters, the RPM, so many parameters. So if you want to look at, each one of these parameters, and at every level of the value of each one of these parameters, let's say, you want to look at the, the fuel flow rate. So you can vary fuel flow rate over a large range, right? Or you want to vary temperature, you want to vary the pressure. Now, if you keep doing experiments for each of these parameters at every value, you'll be doing basically, and you'll end up with doing infinite number of experiments, right? Which may not be required. So one of the goals of the experiment should be to get maximum information about a system with minimum number of experiments. Okay. So there, this design of experiments become important. Okay. So when you talk about design of experiment, there are two different approaches we are going to talk in this class. One is the full factorial design. The other one is 2 to the power k factorial design. What is full factorial design? So let's say you are talking about the engine performance, and you are talking about 5 different RPMs, 5 different let's say temperatures, and 5 different pressures. So you'll have RPM 1, 2, 3, 4, 5, temperature 1, 2, 3, 4, 5, and pressure 1, 2, 3, 4, 5, right? So if you want to understand each value of each of these 3 parameters, the effect of each value, each of these 5 values for each of these parameters, you would basically end up doing 5 cross 5 cross 5, 125 experiments. Okay. So you end up doing large number of experiments. In general, if you generalize full factorial design, let's say number of factors affecting the performance, number of factors affecting the performance is, let's say, k, and number of labels for each factor is, let's say, ni. Like here it is 5, right? 5 different levels of RPM you want to investigate. The total number of experiment that you have to do is basically n is multiplication. This is the multiplication symbol, not summation. I equal to 1 to k ni. So this is basically n1 into n2 into n3 up to your nk. Okay. So typically this approach is not preferred because you don't want to spend effect of each of the labels for each of these parameters to really understand the system. What is advisable is that whether all these parameters have equal influence on the performance, or certain factors are more important, certain factors are less important. Okay. Let's say you find that effect of temperature is not that significant, whereas the effect of RPM is very significant. Okay. So really you can do many different levels for RPM, and temperature maybe you just do only 2. So this is the objective of 2 to the power k factorial design. It will help you in deciding which factors have significant influence on the behavior of a system, and basically identify those factors. That way you will be able to reduce the total number of experiments that you may have to do to completely comprehend your the system that you want to understand. So in 2 to the power k factorial design, let's say you have k different factors. And initially, for each factor, you try with 2 labels. You do some preliminary experiment to know what is the impact of each of these factors. So let's say some high and low. High you assign with a value 1 and low you assign with a value -1. Okay. Now this 2 to the power k factorial design will help you in determining which factors are more important so that you can reduce the number of experiments. It will also help you the knowledge of interaction effect, like for example, this temperature and this RPM has a strong correlation, or this temperature and this RPM has a strong correlation. Whether RPM temperature have stronger correlation or RPM pressure has stronger correlation. Okay, so it will help you obtain knowledge of the interaction effect. So knowledge of So let's say we take an example. We say that k equal to 2. Okay, and let's generalize the factor. Let's say the factors are xa and xb. So if you take a full factorial design, if you designate the experiment number and xa, xb, 1, 2, 3, 4. So you have to do xa high value, xb high value, xa low value, xb high value, xa high value, xb low value, and both are low values. Okay, so you have basically 4 different experiments you can do, and each one of these experiments, let's say, give you some outcome in terms of the performance. Let's say it could be efficiency or work output or whatever. Let's call these are y1, y2, y3, and y4. Okay, these are the outcomes. Now we can put these in an outcome matrix. Okay, so we can construct an outcome matrix in this way. So we put in this direction, let's say we say xa. In this direction, let's say it is xb. So I have let's say in this direction I have xa high value, low value, xb in this direction high value and low value. So from the previous slide, you can say the outcome when xa and xb are high, the outcome is y1. When xa is low, xb is high, let's call it y2. When xa is high and xb is low, let's call it y3. And when both are low, let's call this outcome as y4. Okay. Now we can actually have a regression model to describe the relationship between the y's, that is the outcomes, and the x's, which are the input. Okay, so we can construct a simple regression model to relate yi's with xi's. So how do we do that? We use a regression equation. So in this case, y is a function of, rather yi is a function of xa and xb. So this is like the multiple regression that we just talked about. Like we wrote, right? Z equal to ax plus by plus c. Similar to this. And here we write that, let's say y is some constant p naught plus pa xa plus pb xb, plus there is an additional term which represents the interaction effect of xa and xb when both vary simultaneously. Okay, so that we denote with a fitting parameter pab xa into xb. So this is the regression model that we have to work with. And the p's are basically the regression parameters. So these are all regression parameters that we need to evaluate. And the PA basically talks about effect of parameter xa, PB talks about effect of parameter xb, and PAB signifies the interaction effect. Okay. Now, if you substitute these values xa and xb, and y1, you can write that y1 equal to p naught. So for y1, xa is 1 and xb is 1. So pa plus pb, and pab is multiplication of xa into xb. So that is 1 into 1 in 1. So pab into 1. That is your equation 1. Okay. Y2 is here. xa is minus 1. So p naught minus pa. xb is 1. pb. So when xa is plus 1, xa is minus 1 and xb is plus 1, xa into xb will be minus PAB. Right? This is y2. Similarly, y3 will be equal to p naught. xa is plus 1, so pa. xb is minus 1 minus pb. Plus 1 minus 1, so you get minus ab. y4 will be equal to p naught. xa is minus 1, so minus pa. XB is -1 minus PB, and both are -1. So the product will be positive. It will be plus PAB. So you have 4 equations and 4 unknowns. Okay, so you can easily solve for P naught, PA, PB, and PAB. So you will have the model which represents the regression between the outcome and the dependent variable. Okay, and you can see from here that your P naught is nothing but the mean of all the y's, y1, y2, y3, y4 divided by 4 will give you P naught. So you can see from here, PA minus PA will get cancelled, PA minus PB will get cancelled, PB minus PB will get cancelled, PB minus PB will get cancelled. Similarly, plus PB minus PB minus PB plus PB. So if you add all the right hand side, you will have 4 times P naught. Here y1 plus y2 plus y3 plus y4. So P naught will be y1 plus y2 plus y3 plus y4 divided by 4. Now, basically, if you represent in a graphical form, let's say this direction is XA and this direction is XB, you will have basically 4 points here, depending on which one is plus, which one is minus. So here both are plus, here XA is plus, XB is minus, here both are minus, here XA is minus and XB is plus. Okay, so essentially you have a region something like that, and this representing the 1, 1. This is -1, 1. This is 1, -1, and this is -1, -1. And this is basically 0, 0, which is nothing but your P naught. Because if you substitute PA and PB to be 0, then you will see that this will not, the origin will not be nothing but y1 plus y2 plus y3 plus y4 divided by 4. So the variance of the data, you can find out the variance of the data S y square will be basically yi minus the mean, basically P naught square sum divided by n minus 1. So this will represent the variance of the data when you get this correlation. Now, depending on this, here we have, let's say, 4 parameters, y1 minus P naught square over n minus 1. Similarly, y2 minus P naught divided by n minus 1 square. So you have basically 4 different terms on the right hand side. Whichever is higher, that term would have a highest influence on the outcome. Okay, so I will stop here because time is up, but in the next class I will take an example, and we would really work through and identify the most critical parameters and find out the variance to actually identify which factor is most influencing.
Thank you, sir.
Sir, one request. Can you please share the 5th page?
Sir has left, yeah.
Oh, he has left. Okay. Can anyone share the 5th page, page 5, snapshot?
I will share. I will share later in the evening.
Okay, sure. Yeah. Thank you.
5th page, right?
Yeah, 5th page. Yeah. Thank you. Right.
Recording stopped.
Who is recording?
Not sure. Yeah.
The recording is at the IITM side.